In this short video, we're going to discuss the plane polar coordinates. And in particular, we're going to look into the mathematical expressions of three of the dynamical variables that appear in physics and classical physics, namely position, velocity, and acceleration, how they appear in plane polar coordinates. Now, before doing so, I have to first of all define what the plane polar coordinates are. So we would start with the familiar Cartesian system of coordinates. I should mention that plane polar coordinates are used to describe the points on a two-dimensional surface. It is not a three-dimensional set of coordinates. So we'll just look into the two-dimensional Cartesian plane and see how we can get the or define the plane polar coordinates. So as you all know, I can identify any point in the two-dimensional plane, such as point P, by a set or a pair of numbers, which I would name x and y. X would be the horizontal distance of this point to the center of our coordinate system, the origin of our coordinate system, and y would be the vertical component or the vertical distance of that point P from the origin. Now, in order to transfer to the polar system, all we have to know is the distance. We need, instead of two numbers, we need a distance and an angle. The distance is defined as the distance between the origin and the point of interest, which I would show by r, and the angle is the angle that this r makes with the positive x-axis, and it's customary to show it by theta. Usually we call r the radial distance, and theta the azimuthal angle. All right, now through a set of transformations, I can start with Cartesian coordinates and convert them into polar coordinates and vice versa. So with applying simple trigonometry, it's easy to show that the x coordinate can be written as r times cosine theta, and the y coordinate can be written as r times sine theta. So if you have the two polar coordinates theta and r, you can end up with the Cartesian coordinates through these equations. Likewise, I can find my polar coordinates by knowing the Cartesian coordinates in this way. So the radial distance would be the square root of x squared plus y squared, and the azimuthal angle would be the inverse tangent of y over x. All right, so far so good. Now we would like to define unit vectors in the plane polar system. So again, instead of working with x and y, we're going to work with r and theta. And for that, we need to define two unit vectors. The first unit vector is the unit vector which shows the direction of the point with respect to the origin. If I were to show it here, so I don't want to make this figure too busy, so I would just draw another, quickly draw another system here so that I can easily show this to you. So let's say this is my point P, and these are the polar coordinates, r, the radial distance, and theta, right? Okay, now the unit vector that is associated to the radial distance would be a vector in this direction, and we'll show it by r hat, and the unit vector associated to the azimuthal angle would be perpendicular to the radial unit vector, and it will be in this direction. I will show it by theta hat. R hat and theta hat are always drawn in the direction of increasing r and theta. That's the way to, that's the way that they are actually defined. Now, there's an important difference between the polar unit vectors and the Cartesian unit vectors. For a reminder, the Cartesian unit vectors are along the two Cartesian axes, x and y. And in this figure, I can show the unit vector along the x direction as x hat, and the unit vector along the y direction as y hat. As I mentioned, there's an important difference between r hat and theta hat and x hat and y hat. And that comes from the fact that in the Cartesian system of coordinates, the unit vectors are constant in direction, whereas for the polar coordinates, the unit vectors are not generally constant in direction. In fact, both of them are functions of the azimuthal angle. So we must bear in mind that r hat is a function of the azimuthal angle, and theta hat is also a function of the azimuthal angle. If I look into different points in this space, in this two-dimensional space, I would end up with different directions of r hat and theta hat. So for instance, if I look into this point, r hat would be in this direction, and theta hat would be in this direction. So this is the way that these two unit vectors actually depend on the azimuthal angle. Okay, I think this is enough for the introduction to the plane polar coordinates. Now let's go to the physical problem of defining position, velocity, and acceleration in the plane polar system. Well, for position, you can easily identify the position of any particle in the plane polar system by looking at the direction it has with respect to the origin. In other words, you have to look into the position vector. That gives you the position uniquely. So what is the position vector? It's the vector that connects the origin to the location of the particle. So this would be my position vector. And since this is along the radial direction, I can actually write down the position vector in this form. You can say that r is nothing but the radial distance times its direction, which is along the radial unit vector. Okay, so any object on the two-dimensional plane can be uniquely identified with this position vector. Okay, so just to let you know, I'll write this here. This is called the position vector. Okay. The next dynamical variable that we're interested in is velocity. And we all know that if this particle, this point P, if it's going to represent a particle and it starts to move, let's say it moves along some certain path, then I can define a new vector which indicates its velocity. And the velocity is always tangent to the trajectory of the particle, right? So let's say if the particle is moving in this direction, this would be the velocity. And the reason that it's tangent is because velocity is nothing other than the time derivative of the position vector. So I'll write that down here. So we know from classical mechanics that the velocity of a particle is defined as the time derivative of the position vector. If I take another derivative, if I take the second derivative of the position vector, I would end up with acceleration. So acceleration is also defined as the second time derivative of the position vector, or in other words, the first time derivative of the velocity vector. Okay, so these are the dynamical variables that we're going to study. Well, the position vector is already given in terms of the polar coordinates, so I'm not going to do anything further with the position vector. It's the way that you show it in the polar system. We will start now with velocity. So for velocity, we would say, well, we'll use the definition. It's the time derivative of the position vector. And here we will start with our calculations in order to find a way to express the velocity vector. So let's see how we can do that. I'll bring this here. The velocity is the time derivative of the position vector, but the position vector itself is given in terms of the radial distance times the unit vector and the radial direction. Now, according to the product rule in differential calculus, this would equal to the time derivative of the radial distance times the unit vector r hat plus the radial distance times the time derivative of the unit vector in the dot and the r direction. Now it's customary in physics to show time derivatives by the symbol dot. Okay, so if I have, let's say, a variable, for instance, let's say I show it by a. The time derivative of a with respect to the derivative of a with respect to time. In classical physics, we can show it by a dot. This is just the compact form of showing it. All right, so we don't need this anymore. So if I use this, change of notation, then my time derivative of the radial distance here would be given by r dot. So I have r dot here and then times r hat plus r. What is the time derivative of my unit vector along the radial direction? Well, remember, the polar unit vectors change. And in physics and classical physics, everything changes ultimately as a function of time. I mean, the ultimate independent variable in physics is time. So all the dynamical variables would change in time. So I would like to know how the unit vector in the r direction changes with time. And in order to do that, we have to consider the fact that the r hat unit vector depends on theta. So the changes of r hat with respect to time must come from the changes of r hat with respect to theta and the changes of theta with respect to time. In other words, I can take this and look into the time derivative of r hat by using the chain rule. That'll be the derivative of r hat with respect to theta times the time derivative of theta. Now, how r hat changes based on theta, we can easily show, and I'm going to do that in a future video, that the changes of r hat with respect to theta would be in the direction of theta hat. So dr hat, d theta is nothing but theta hat. And d theta dt is just theta dot according to our notation. So this would be theta dot theta hat. So I can take this dr hat dt and write it as theta dot theta hat. All right, now I end up with an expression for my velocity vector in the polar coordinates. So I'll write it down, the final form. V, the velocity vector, would be r dot r hat plus r theta dot theta hat. So as you can see, the velocity vector in general has two components. The component along r hat is what we call the radial component of the velocity, which we show it by VR. And the component of the velocity vector along the azimuthal direction is what we call the tangential component of velocity, or the tangential speed. So in other words, I can write V in terms of a radial velocity and an azimuthal or tangential velocity. Notice that the units are consistent in both cases. In both cases, they would be given in terms of meters per second. Okay. Let's move on to the next derivative, which gives us acceleration. Let's see how we can find an expression for that. So here's the acceleration. As we know, the acceleration is the time derivative of velocity. And therefore, I'll just take the time derivative of what we got for velocity and polar coordinates. All right. Now, again, we'll use the product rule and some rule of differentiation to find out. So we have dr dot dt times r hat plus r dot dr hat dt plus dr dt theta dot theta hat plus r d theta dot dt theta hat plus r theta dot d theta hat dt. So I end up with 5 terms here. And let's see how to simplify them. So the first derivative is just the second derivative of position with respect to our radial distance with respect to time. I can show that by r double dot. Remember, each dot represents a differentiation with respect to time. So I have r double dot r hat for the first term. Here I have r dot. Well, what was the time derivative of r hat? We actually calculated the time derivative of r hat as theta dot times theta hat. So I'll replace that by theta dot times theta hat. And then here, I have the first derivative of r with respect to time. So it's just r dot. And then there's a theta dot theta hat here, plus r. What is the time derivative of theta dot? Well, it's the second time derivative of theta. So that will be theta double dot. And then here we have a theta hat. And then here we get r theta dot. But what is the time derivative of the polar unit vector? Again, just like the case we worked out for the derivative of the radial unit vector, for the polar unit vector, we'll do the same. We'll look at the same procedure. So we have d theta hat d theta. That would be, let's say, if I want to calculate this, let's find out how theta hat changes with time. I would have to first find out how theta hat changes with theta, and then multiply it by the changes of theta with respect to time, according to the chain rule. Now again, it can be shown that the rate in which the polar unit vector changes with angle gives me minus r hat. Okay, as I said, I'll show these in another video. So for now, accept this, that r hat changes with theta with the rate of theta hat, and theta hat changes with the theta with the rate of minus r hat. And this one, well, you know that this is theta dot, so the rate in which theta hat changes with time is just minus theta dot r hat. So I'll go back here and replace this by minus theta dot r hat. Okay, so let's see if we can simplify things further. So I'll just write one more step here. First of all, we can see that these two terms are essentially the same. So that gives me 2r dot theta hat. And this last term here, I can write it as minus r theta dot squared r hat. All right. Now, if I factor the unit vectors here in the radial direction, I would have an r double dot from the first term, and from the last term here, we have a minus r theta dot squared. On the other hand, the second, third, and fourth term, they all contain theta hat, so I can factor the theta hat there, and I end up with 2r dot theta dot plus r theta double dot. And that gives me the expression for the acceleration vector. So at the end of the day, the acceleration vector can be written in polar coordinates as follows. A would be r double dot minus r theta dot squared r hat plus 2r dot theta dot plus r theta double dot theta hat. All right. Now, just as we did in the velocity vector, here, the component, the radial component of the acceleration, we call it, we usually show it by a sub r. It's the radial component of acceleration. It's the acceleration towards the center. And the azimuthal component, which is this one, we call it a t, a tangential component. And therefore, we can write a in terms of a radial component and a tangential component, just like the way we did for the velocity vector. So let's put everything all in one package together. So first of all, r, the position vector, was given by this simple relation. The velocity vector was given by this relation, r dot r hat plus r theta dot theta hat, r dot r hat plus r theta dot theta hat. And the acceleration vector is given by this expression, r double dot minus r theta dot squared r hat plus 2 r dot theta dot plus r theta double dot theta hat. Okay. Now that we've found out the forms of the position, velocity, and acceleration vectors in plane polar coordinates, we can do classical physics with them. As an example, let's say I want to find out how Newton's second law looks like in plane polar coordinates. I'll use a simple form of F equals ma So if I want to express this in the plane polar coordinate system, well, that would give me a structure like this. So the radial component of my force would just be M times R double dot minus R theta dot squared. And the tangential component of my force would be M to R dot theta dot R theta double dot. As another example, let's look into, for instance, the form of the kinetic energy of a particle T in plane polar coordinates. Well, the kinetic energy is just 1/2 mv squared. So I can write this in terms of the plane polar coordinates as 1/2 m times the square of the velocity. If the velocity has two components, and you know that r hat and theta hat are perpendicular unit vectors, right? So that's why they can define the two-dimensional plane. So that'll be r hat squared plus r squared theta dot squared. That'll be just r dot squared plus r squared theta dot squared. So you can find countless of examples in which you can express all the dynamical variables of interest in terms of the polar components. Now, why did I even want to look into this topic is that during the next 3 or 4 lectures, I'm going to discuss the planetary laws of motion, namely Kepler's planetary laws of motion and the problem of central force. And when we look into those, we would find out that the plane polar system of coordinates is the most suitable way to describe planetary motions. And in particular, we're going to look into the orbits of planets around the sun. So that's why I just wanted to introduce you to these new notations and also these alternative ways of expressing the position, velocity, and acceleration. If you have any questions about this short video, any comments you would like, please leave them on the comment section. And don't forget to subscribe to my channel and stay tuned for the next video, which we would start analyzing and considering the very important, let's say, chunk of the history of physics or history of science, which is the discovery and explanation of the planetary laws of motion. So until then, take care of yourselves and see you next time.